Okay, so I wanted to start off with making a small Kubernetes mini-series about what Kubernetes is, how to use it, and then going into some practical examples where we'll actually set up a website with a front end and a back end and be able to expose it to users on the internet. So in this first video of the series, I wanted to start with what Kubernetes is and how it's structured. So Kubernetes is basically a tool that people use to run several instances of containerized applications. So the smallest unit of abstraction in Kubernetes is called a pod. So a pod is typically thought of as typically it'll be one Docker container running on some machine. In Kubernetes, we don't care if this machine is a virtual machine, a server rack, it's a personal computer, it doesn't matter. For all we care is that there is a pod that can connect to the internet and it can connect to other pods in our Kubernetes cluster. These are the two most important things for pods. First, the pod must be able to connect to other pods. In Kubernetes, we assume that things are typically running within a computer for development environments or within a large server where all of the pods are interconnected. Another feature of pods is that they must be stateless. That means that any logic that keeps track of something like a database, maybe you want to store users for an application. If you're running a video game server and you want to keep track of, say, the scores of two players, these pieces of data should not be stored in pods. Instead, we'll talk about other ways that Kubernetes allows us to define storage space that persists across pod creations, deletions, and updates. But for now, the most important part is that pods must be stateless. If we store memory in a pod and we decide to keep our scores, let's say, in memory, then if the pod is deleted or if the pod is rescheduled, all that information will be lost. So therefore, any data that we expect to persist for the duration of our application cannot be stored in the memory of a pod. Another thing is that pods are typically composed of a single container for our purposes. In real-life applications, they can contain multiple containers, but for us, we'll mostly be dealing with pods that run one container. In reality, Kubernetes allows you to run any number of containers in a pod, as long as those containers are all stateless. However, the reason you won't want to run too many containers in a pod is because these containers share an IP and networking space. So if you have two containers running in a pod, you'll have to manually ensure that they do not bind to the same port or access invalid IP addresses. So these containers share the same space on a computer, and they can talk to each other using localhost. So if we ever have two pods on a single machine, they can be running, communicating via localhost. They also have a shared pool of memory and storage, and we can again allocate permanent storage if we want these pods to persist data for the duration of the pod. But again, pods are mortal, and so anytime a pod is deleted, which will be frequently in our case, all of our pod data will be lost. So we don't want to keep mission critical data stored locally on a pod. Now, typically in Kubernetes, we won't be dealing with individual pods. While pods are useful and we can define templates for them, what we'll really be dealing with is our next object, which is a deployment. So a deployment in Kubernetes is kind of a master controller that orchestrates a bunch of pods. So if you think about a pod as a single indivisible unit, a deployment controller will orchestrate and oversee a bunch of pods. What this means is that if one of these pods is to fail, let's say one of our pods crashes due to a memory issue, then the deployment will see that this pod has failed, and then it will create a new pod to replace it. So deployments are typically units that we'll be dealing with in Kubernetes because deployments allow us to ensure that any number of pods is always going to be running at the same time. So if we want to ensure that, for example, we have 5 instances of our web server running, we can create a deployment, set the replicas to 5, and then the deployment will ensure that we always have that many pods running in our system. Of course, there can be temporary fluctuations, like if a pod goes down, it'll take a few seconds for the next pod to be created. But in general, if we want to have pods that are long-running, or not that the pods themselves are long-running, but if we want to have a long-running guarantee that a certain number of pods are running, we're going to be using a deployment. Internally, what a deployment does is it creates a Kubernetes object called a replica set. We won't be dealing too much with replica sets, but they provide a more low-level way to orchestrate a number of pods. Typically, the preferred way of creating a number of pods is through a deployment, but for some more specific requirements, a replica set can be used instead. The final important object that we'll be dealing with commonly is called a service. So we talked about deployments, which are ways to guarantee that a certain number of pods are running and to ensure that those pods are recreated if one goes down or if one becomes unavailable. A service is going to allow us to communicate with those pods. So you can think of a service as managing access to a deployment or a set of pods. Services typically don't communicate directly with the deployment object, but typically what we'll do is we'll have a pod template that's run by a deployment, and then we'll have a service that manages access to it. Now, a service is what allows us to communicate with the pods without knowing about the individual IP addresses of the pods or where they're located, or having to think about exactly which pod we're communicating with. Services are excellent if we have several pods that provide the same function, but for which we don't care about which exact pod is chosen. So, for example, let's say I'm on my cell phone and I want to connect to a website that's running, say, 20 instances of an HTTP server serving the website. I don't really care about which server I communicate with. All I care about is that one of the pods gets my request and responds to it. And ideally, we'd like these to be load balanced. So if many people are using our website, we'd like each of the pods that provide our website to get a fraction of the load. And Kubernetes will do this somewhat automatically for us with the creation of a service. So when I go to a website using Kubernetes that runs Kubernetes on the back end, I'll typically be routed to a service that provides an abstraction over a set of pods, and then one of these pods can respond to my request and send the data back to my phone. Now, this diagram is a little bit oversimplified. There are several steps before we reach communication with the service, such as dealing with an ingress controller and things like that. For now, we won't worry about that, but that is important in how we can ensure that our cluster is connected to the internet and that people on the internet can only access the portions of our cluster that they are meant to access. But for now, what we can think of a service is, we can think of a service as simply a set of pods that provide the same functionality and for which we don't care about which exact pod is chosen when we connect to it. Now, so let's talk briefly about how exactly we can connect to a service. So a service will get a virtual IP address, and other pods in our cluster can access this virtual IP address. It's very important to note that this is only within our cluster. So someone on the internet cannot just go and access this IP address and expect to be connected to our service. This is only for pods within the service. And Kubernetes provides a DNS add-on that ensures that when you try to do a lookup on the name of the service, you will get the virtual IP associated with the service. So for example, if I do a DNS lookup on simply the service name, this will resolve to the virtual IP address of our service. Now, this is assuming that we're in the default namespace. We haven't talked much about namespaces, but in case you are using namespaces in your own Kubernetes cluster, if you need to access a service within a namespace, you can do service name.namespace and access the service through that DNS name. Now, once we connect to this IP address, one of the pods associated with the service will respond to our requests. Since Kubernetes doesn't give us a way to talk to a pod individually through a service, it's important that whatever pod responds to our request is able to handle the request. Typically, we'll have services where all the pods are of the same type and provide the same code, but this is not necessarily always the case. So let's talk about the services that Kubernetes provides for us. The most basic type of service is called a cluster IP. A cluster IP service means that the service is assigned a single IP address that can be connected to from within our cluster. If you're interested in the details, any service on the cluster can be connected to by any other node on the cluster, but the exact rules for connecting may depend on the settings of namespaces. But again, we won't get into that in this mini-series. The second type of service is called a node port. What this does is it allocates a fixed port on each node that the service is running on. So If the node that's running the service is accessible from outside the cluster, then by visiting the node's IP address and at the node port, the service will be accessible from the internet. This is a good service type to use if we want to debug our service from a local machine. So if you're running, let's say, Kubernetes on Minikube, which is a tool that allows you to emulate a Kubernetes cluster with one node, which is your local computer, the node port service is what you're going to use, because the node port service will create a port on your local virtual machine that's running Minikube and allow you to connect through that port to the service. However, this may not be practical for large settings where we have thousands of nodes running a service and we want to be able to connect to all of them, in which case it would be a pain in the neck if we had to somehow find the node IP address for every single node in our cluster that's running the service and then somehow make those public and provide load balancing. So to provide a load balanced service, Kubernetes gives us the load balancer type. The load balancer type is a service type that creates a load balancer object and allows Kubernetes to pick IP addresses for particular nodes or pods according to some algorithm that you can specify. Also, this load balancer service is internally creating a node port and a cluster IP service, but that won't be too visible to us because Kubernetes hides those away. The most important thing to note for the load balancer type is that it's typically implemented by a cloud provider. So if you're running Kubernetes on Google Kubernetes Engine, for example, when you create a load balancer type service, it'll be up to Google's cloud infrastructure to allocate a public IP address for your service and then to implement load balancing. This typically will incur some cost to you for running on the cloud provider because you're going to be eating up an external IP address. However, since for now we're going to be focused on local development environments and not worried too much about load balancing across thousands of nodes, we're not going to use this type of service as much in our mini-series. Alright, thanks for watching this video. If you enjoyed, please give a thumbs up, and I'll see you in the next video on Kubernetes. Until next time, keep it out.